Our next speaker is Caitlin Witter from Purdue University, and she did her practicum at Lawrence Berkeley National Lab.
Okay, is this on? Okay, great. Hello, everybody. My name is Caitlin Witter, and my talk is on physics-informed prediction of molecular properties using a graph convolutional network. And this is joint work with my PhD advisor within the School of Computer Science at Purdue University, Alex Pothen, and also Drs. Yuheng Tang and Aiden Bullich from Lawrence Berkeley National Laboratory. All right, so to provide a little overview of the talk, I'm going to talk about background information, then go into methods, discuss our results, and then finally arrive at conclusions. So this is our research contribution, PILNet, which stands for Physics Informed Loss Network. And what we did with this is we created a graph convolutional network capable of predicting molecular properties. And how we do that is we incorporate physics into the optimization step of training, which will be detailed later on. And we use a non-equilibrium data set that is a non-energy minimized data set, which renders the problem a little bit more challenging and also allows us to reach a larger area of the chemical space. And we were able to predict these properties with high accuracy and using very little training data, which corresponds to low training time. So to motivate the problem a little bit, in certain disciplines, such as drug discovery and material sciences, there is a need to identify molecules with specific properties, or perhaps properties within certain ranges. But the problem is that some of these properties, using your traditional quantum chemical calculations, it can be computationally prohibitive. In fact, time to complete DFT, depending on the level of theory, can scale as cube of number of electrons, or even worse. And this can lead to calculations taking several days per molecule to reach the desired chemical accuracy. So just to define partial charge a bit, so it's a fractional charge resulting from an asymmetric distribution of electrons in a molecule due to unequal electronegativity. So if you look at the right, here's a water molecule, and the oxygen is more negatively charged, as you see, because the electronegativity is much higher, so it tends to hoard electrons. And then to define this chemical accuracy property, it's a consensus error that the chemistry community decides on a particular property. So for the specific property we're going to talk, partial charge, talk about in this talk, it's 0.01 elementary charge units. So in our training, that's our desired number that we're trying to hit. So just to provide a basic overview of what a graph convolutional network is, it's a neural network architecture for performing machine learning on graphs. So in order to get your output predictions and going from the input data set, you have these features, and they're transformed through multiple passes through these convolutional layers. And during these convolutional layers, the feature representation of each node is updated based on an aggregation of its surrounding neighbors. So here's just a basic schematic. So you have your input data on the left, and it undergoes various transformations through these layers with the weight and biases. And then you get this prediction as an output step. And then that, along with the true values, go into this loss function, which kind of computes a distance. It tells you how close your predictions are to the data set values that you're targeting. Out from the loss function comes a loss score, and then the optimizer uses the loss score to update these weight and bias matrices and vectors, and then turn this loop cycles on and on throughout your epochs until you hopefully get predictions that are close to your target values. So now to define a physics-informed neural network, it's a neural network that introduces biases in order to guide the learning process towards a more physically consistent solution. And there are a number of ways to implement a physics-informed neural network, but specifically with PILNet, we do this by identifying specific physical laws specific to our the properties that we're predicting and also our data sets. And then we augment the loss function during training in order to get it to come as close as possible to these laws that we've established. So on to the method section. So this is the data set I mentioned that we use. It's called the ANI1X data set. It's a non-equilibrium data set of about 4.6 million organic molecules consisting of elements H, C, and NO. And there's a graph rendering of a molecule from that data set. So now, how are we transforming these molecules into a graph formatting that is useful for input into our network? So if you're not familiar with a discrete graph, on the right, that's an example. And here we are modeling the atoms of the molecules as nodes of the graph, and we're weighting the edges by interatomic distance using this kernel that will be detailed on later slides. Also to note that we're representing these molecules as complete graphs, unlike this distribution, or sorry, this depiction. in order to retain as much information as possible, but we still distinguish between the different values of the edges by using this weighting function that I will describe in a second. So here's kind of an overview of the dataset preprocessing pipeline. So you have your Ani-1X molecule, and from that dataset you also have nuclear charges and atomic positions. To the nuclear charges we apply a one-hot encoding, so basically we have a bit vector, and we set a bit depending on what kind of element that we're referring to. That gives us the node features. And the reason why we do this is so that we can show the network this is categorical data, so we don't want the network to decide that carbons are more important than hydrogens because of their different scaling. Then for our atomic positions, those are represented as Cartesian coordinates, and we apply the squared exponential kernel, which I promise is on a later slide. But from that, we get a weighted interatomic distance, and then we apply a normalization to get the edge features. And this normalization is so that the edge features aren't wildly larger than the node features, and the model decides that the edge features are more important solely based on their magnitude compared to the node features. So here's the squared exponential kernel, just to briefly go over it. The input are the atomic coordinates, and the closer that these atoms are in space, the larger this kernel value will be, and the farther they are in space, the smaller this kernel value will be. So here's an overview of the PLNet architecture, and there's a circle around this module because on the next slide we're going to zoom into it and discuss that in further detail. But the input features go through this module and they get subsequently updated until you go to this green output layer that gives you the predictions. And like before, the predictions and the true values are inputs into this loss function. But in addition to what I showed you earlier, we have this step where we compute the penalties from the predictions. And the loss function will be on shortly it'll be on a later slide. But in those three, the predictions, the penalties, and the true values go into the loss function until you get this loss score. And like before, the optimizer updates the weights on the layers and also within the loss function based on the loss score. So zooming into the module, you have your node features and edge features that are input into it, and the node features and edge features are expanded in order to establish patterns within the data. These numbers, for example, the dimensions of 32, 64 that you see, and also the skip connection at the end, we got those values from various ablation studies that we did, but I don't have time to detail them in the slides. But we did various studies to tune the hyperparameters and make sure that they're the best for the network. So the nodes and edge features get expanded twice using linear functions and also a nonlinear activation function. And that CELU function is very similar to ReLU, but it's continuous everywhere. Then once they're expanded, they go through this graph convolution function where essentially you take the node features and you form a Hadamard product with all their incident edges. Then for the next green portion, you get the output of this combined node edge representation. You undergo two more, an expansion and compression of these features. And you compress it to C, which is the original node feature dimension. So in the yellow step, you can combine the node features with this expanded representation. That's called a skip connection, and that's also something we tested in these ablation studies. And then from there, you get the updated features. And depending on which module this is, it either gets, updated features either get fed into the next module or they get fed to the output layer to form the predictions. So this is the activation function that I mentioned. And here's the graph convolution step. Like I said, you form a Hadamard product with the node features and their incident edges. And then here's the loss function. So the base loss function that we're using is called mean squared error. It computes a distance between the predicted and target values. But then we add this physics-informed component to it. So depending on what your penalties are, for this case, it's node level prediction, so it'll be for each node. You take an absolute value of those penalties, depending on the penalty type, and you sum over them. And then we have this weight function. That's another learnable weight that we have within this network. And we have this weight. This weight is multiplied by these penalties because these penalties have different scales. So we want to adjust for scaling for that. And also the network can determine the importance of the penalties relative to each other. And then to that weight scalar value, we applied a sigmoid function so we can constrain the value between 0 and 1 because we don't want the weights going to negative values and you end up with a negative loss score or the weights exploding, for example. So specific to our data set, these are the penalties that we came up with. So for example, the charge sum penalty, we want the sum of the individual partial charges that we predict to equal the net charge of the molecule. So we can penalize by the distance from the net molecule. There's also a certain range of values that it should have according to the element type. So we penalize based on that. And also the hydrogen and the oxygen should be positive and negative respectively. So going into the results section. So like I mentioned, there were a number of hyperparameters that we tuned that you saw in those earlier schematics. There are a number of tables I could show to show respectively how they perform compared to others, but I'll skip over that slide. And then here's some additional details of note. For each of these experiments, we used a maximum training time of 6 hours, but most of them stopped well before 6 hours because we implement early stopping determined by validation loss. So basically we have this patience of 100 epochs, and if within 100 epochs either the validation loss doesn't improve, the minimum validation loss, or the median doesn't improve, then we stop early. We stop training early. And then I'll note that we ran these codes on a single GPU on the Gilbreth Community Cluster at Purdue University. I'll hit on this a little bit later, but parallelism is something that could easily be incorporated into this. But because the data set size isn't too large and the molecules aren't very large, it wasn't necessary, but it's definitely something that could be incorporated in the future. So here are the main results. So the tagline is PLNet predicts partial charges on non-equilibrium data sets at the level of chemical accuracy using less than 6% of the data set and fewer than 6 hours for training. So if you look at the table, there are 3 training set sizes that we have, including the validation set size, which is consisting of 5,000 molecules. And within each of these rows, this is an average over 5 different repetitions of the experiment with different splits of the data set. So if you look at the MAE column, all of these numbers are below that 0.01 chemical accuracy number that we were targeting. And also the accuracy is improving with the increasing training set size. Looking at RMSE, the values are similarly quite good in R squared, which shows sort of how correlated the predicted values are with the training, with the test data set values. And that's high, which is ideal. And also, like I mentioned, the training time is all under 6 hours, and in fact, the 2 smallest training sets, they end substantially earlier than that. And then in the paper that we have for this work, we compare PLNet with a number of different machine learning techniques for predicting partial charges, but here's one that's the most similar to ours because of the data set. They use the ANI1X data set as the basis for their training set. But they do expand it to include molecules with other elements like chlorine, I assume. I remember it's chlorine and some other ones. So essentially we have similar comparable training accuracy, but our training set size is much smaller. Our largest one is 250,000 graphs, whereas theirs is 9 million. And also our training time, like I said, capped at 6 hours, but they use 270 hours of training time. So that was a good result. And then this is just an alternative view. So it might be a bit hard to see, but each graph, each plot corresponds to a different training set size. And then the colors within each respective plot corresponds to an element type. And then the left is our mean predicted value for partial charge, and the right is the data set, like true value for partial charge. So you notice that they're quite level throughout. So it's another view that our predictions are very close to what they ought to be. Same for the standard deviations, they're quite similar. And as an added bonus, the hydrogen and carbon partial charge is positive, and nitrogen and oxygen is negative, as would be expected. So to conclude and talk about future work, discussing training set size, one thing we could do is increase the training set size for potentially greater accuracy, as there was a trend. As we were increasing the training set size, the accuracy was getting better. But another option is we could decrease the training set size when less training data is available, while still maintaining chemical accuracy potentially, since we had some wiggle room there. As I mentioned before, we could incorporate parallelism during training in the size and/or number of graphs. That is, if we decide to use a much larger training set with much larger molecules. And also, another option is we could simultaneously predict additional molecular properties. So in this work, for example, we just predicted partial charges by itself, but we could predict perhaps atomization energy and partial charges together, and then training one could help the training of the other one, since they would be interconnected. So with that, I'd like to say thank you to DOE CSGF and the Krell Institute. It's been a great 4 years, and I've enjoyed every minute of it. And also, thank you to these people from Purdue University, including my advisor that I mentioned, Professor Alex Pothin, and also, once again, Dr. Yuang Tang and Dr. Aiden Bullich, who I worked with at Lawrence Berkeley National Laboratory. And then I just included some references, and yeah, that's all. Thank you.